Modules and homological algebra, lecture 24, problem session. Problem 1. Check that the following sequence, where Z16 is in the homological position 4, is a complex and determine its homology. We have 0 goes into Z, then multiplication by 4 maps it into Z, then multiplication by 4 maps it into Z sub 8, then again multiplication by 4 maps it into Z sub 8, then multiplication by 4 maps this into Z sub 16, and then this goes to 0. Solution. Let us start by checking that the square of the differential in this sequence is equal to 0. In other words, that the sequence is a complex. In the first non-trivial part, so we have a map from Z to Z and then to Z sub 8, where both maps are given by multiplication with 4. The composition multiplies by 4 times 4, which is 16, and so it sends 1 from here to 16 in Z8, which is 0. So this composition is the 0 map. In the next step, we have the map which starts with Z, multiplies by 4 goes to Z sub 8, and again multiplies by 4 goes to Z sub 8. The composition multiplies by 16, so it sends the generator 1 of Z to the element 16 in Z8, which is equal to 0. So this composition is the 0 map. In the next non-trivial step, we have multiplications by 4 from Z8 to Z8, and then from Z8 to Z16. The composition of these two maps multiplies with 16, and so it sends the element 1 in Z8 to the element 16 in Z16, which is equal to 0. So this composition is also the 0 map. So all non-trivial compositions are 0 maps, which means that this is a complex. Now let us compute step by step all homologies of this complex. In the 0 homological position, this is a position when we have the leftmost Z, we have the left map is the 0 map, so its image is 0 in Z. And the right map is multiplication by 4. This map is injective because it starts with Z and ends up with Z. Any non-zero integers multiplied by 4 gives you a non-zero integer. So the kernel of this map is 0. So the homology, which is the quotient of the kernel by the image, is 0. In the next step, the homological position 1, where we have the second Z, the left map is multiplication by 4 from Z to Z. Its image is 4 times Z. The second map is multiplication by 4 from Z to Z8. The kernel of this map is 2Z, so if we multiply 2 by 4, we get 8, and this is the smallest number. So the kernel is 2Z, the image is 4Z. The quotient of 2Z by 4Z is isomorphic to Z sub 2, so this is the first homology in our complex. The second homology, the homology in homological position 2. So in homological position 2, we have Z sub 8, and on the left, the map 4 times something from Z to Z sub 8, and on the right, the map 4 times something from Z sub 8 to Z sub 8. The image of the multiplication by 4 from Z to Z sub 8 is 4Z sub 8, and the kernel of the multiplication by 4 from Z sub 8 to Z sub 8 is 2Z sub 8. So the quotient of 2Z sub 8 by 4Z sub 8 is isomorphic to Z2. That's the homology of our complex at the homological position 2. Now let us compute the homology at the third homological position. There we have Z sub 8, and the incoming map is multiplication by 4 from Z sub 8, and the outgoing map is the multiplication by 4 into Z sub 16. The image of 4 times something from Z sub 8 to Z sub 8 is, of course, 4 times Z sub 8. And the kernel of the map 4 times something from Z sub 8 to Z16 is 4 times Z sub 8. So we need to have 4 to multiply with 4 to get 16. Therefore, the third homology is 0. It's a quotient of 4z sub 8 by 4z sub 8. That's the 0 abelian group. Finally, we compute the homology at the fourth homological position. There we have z16. The incoming map is 4 times from z sub 8, and the outgoing map is 0. The image of the incoming map is 4 times z16, and the kernel of the outgoing map is the whole z sub 16. Therefore, the whole homology is z16 modulo 4 times z16, which is isomorphic to z sub 4. And this completes problem 1. Problem 2. Consider the following complex. 0 goes to x, then by f to y, and then to 0. Assume that it is homotopy equivalent to 0. Prove that the map F is an isomorphism. Proof. Consider the following diagram. So we have our complex in the top row, our complex in the bottom row. We have the identity maps between the complexes, so the identity from x to x and the identity from y to y. And assume that we have the homotopy map from the upper y to the lower x, which makes the identity map on our complex to be homotopic to the 0 map. As an equation, the condition that our homotopy H makes the identity map on our complex homotopic to the 0 map on our complex looks as follows. So we take the identity map on X and subtract the 0 map, so it should be subtract the 0 map. And this difference should be written as H after F plus the 0 map. So altogether we have that the identity on X is equal to H after F. At the position Y, we have the identity on Y minus the 0 map on Y is equal to F after H plus the 0 map. And as a consequence of the fact that F after H is the identity on Y, and H after F is the identity on X, we get that F is invertible with inverse H. Problem 3. Construct all projective resolutions and injective co-resolutions for simple modules over the path algebra, over the complex numbers, of the following quiver. So we have vertices 1, 2, 3, and 4, an arrow from 1 to 2, an arrow from 3 to 2, and an arrow from 3 to 4. Solution. Recall the following. Simple modules over such quiver are indexed by vertices and are concentrated in the corresponding vertex. Indecomposable projective modules are indexed by vertices and can be described as linear combination of all paths which start at that vertex. And indecomposable injective modules are indexed by vertices and can be described as linear combination of all paths terminating at that vertex. So here are the pictures of all the involved modules. For the simple modules, we have L1, which is one-dimensional at the first vertex, zero-dimensional everywhere else, and all arrows are zeros. L2 has one-dimensional space in the second vertex, and the rest is 0. L3 has one-dimensional space in the third vertex, the rest in 0. And similarly L4. Indecomposable projectives. P1 is one-dimensional at vertices 1 and 2, with the identity map between them, and then the rest is 0. P2, there are no arrows outgoing from the vertex 2, so P2 is the same as L2. P3. From 3 we have an arrow to 2 and to 4, so P3 is one-dimensional at vertices 2, 3, and 4, with the identity maps representing the action of these arrows. And P4 is L4. Now for injectives, no arrows going into vertex 1, so I1 is L1. Vertex 2, there are arrows from 1 and 3 going into the vertex 2, so I2 is one-dimensional at 1, 2, and 3, with the identities representing the action of the corresponding arrows, and it is zero-dimensional at the vertex 4. I3 is L3 because there are no arrows incoming into vertex 3, and I4 is one-dimensional at vertices 3 and 4 with the identity map between these two, and the rest is 0. And now we can draw our projective resolutions. The simple L2 is projective, so its projective resolution is trivial. We have P2 at the homological position 0, and that's it. So at the homological position 0, we have a module which is projective and which is isomorphic to L2. Similarly, L4 is projective, so its projective resolution consists of P4 in the homological position 0. That is it. Now the projective resolution of L1 is the following complex. We have P1 at the homological position 0 and P2 in the homological position -1 with the embedding between them. So P1 is one-dimensional at vertices 1 and 2 and 0 everywhere else, and P2 is one-dimensional at the vertex 2 and 0 everywhere else. So we have a natural embedding of P2 into P1, and the quotient, the homology at position 0, is exactly L1. Finally, the projective resolution of L3 looks as follows. So we have P3, the projective cover of L3 at the homological position 1, and then the kernel of the surjection from P3 to L3 is P2 plus P4. On our diagrams, P3 is one-dimensional at vertices 2, 3, and 4, and here in the vertex 2 we have its image of the projection onto L3. The kernel lives at the vertices 2 and 4, and so it is given by P2 plus P4. Now about injective co-resolutions. L1 is injective, so the corresponding injective co-resolution consists of I1 staying at the homological position 0. L3 is injective, so the corresponding co-resolution consists of I3 at the homological position 0. The injective co-resolution of L2 starts from its injective envelope I2, and then the cokernel is exactly I1 plus I3. So this is our I2, with L2 being a submodule at the vertex 2, and the remaining vertices are 1 and 3. So we take the injective at 1 and the injective at 3 at the homological position 1. And the injective co-resolution of L4 starts from I4, and the cokernel of the embedding of L4 into I4 is exactly I3. This is our I4, this is our L4, it lives at vertex 4, and the kernel of the embedding lives at vertex 3, so it is I3. And this completes problem 3. Problem 4. Consider a short exact sequence of R modules for some ring R. So it starts with 0, this goes to X, and then the morphism I into Y, and then the morphism P into Z, and then to 0. Prove that the following conditions are equivalent. I of X is a direct summand of Y. There exists J from Y to X, such that J after I is the identity on X. And there exists Q from Z to Y, such that P after Q is the identity on Z. Solution. Assume first that Y is a direct sum of I of X and U. Note that I is injective because of the exactness of our sequence at the position of X. Define J from Y to X as I inverse on I of X and as 0 on U. Then by construction, J after I is the identity on X. So the first condition implies the second condition. Now assume the second condition. Assume that J is a morphism from Y to X such that J after I is the identity on X. Denote by U the kernel of J. Then the restriction of P to this kernel is injective due to the exactness of our sequence at the position of Y. Moreover, this restriction is surjective because our sequence is exact at the position of Z. So we can define Q from Z to U as the inverse of this restriction of P to U. And by construction, P after Q will be the identity on Z. So the second condition implies the third condition. Finally, assume the third condition, that there exists Q from Z to Y, such that P after Q is the identity on Z. Denote by V the image of Q. Then the image of I intersects V trivially as only in 0 because P after I is equal to 0, and hence we can write Y as the image of I plus the image of Q, due to the exactness of our sequence at position Y. And this means exactly that Y is a direct sum of the image of I with something. And this completes the solution to this problem. Problem 5. Let R be a ring and M an R module. When R module N, define the trace of M in N, that the sum inside N, the sum is not direct in general, just the sum, of all images of all R module homomorphisms from M to N. Show that trace is an endofunctor of R mod. Show that this functor preserves monomorphisms. Determine whether this functor is left exact. Solution. Let F from N to K be a homomorphism of R module. Given a morphism G from M to N, we have the composition F after G from M to K. And this implies that F maps the trace of M in N into the trace of M in K, not G. F maps the trace, which is given as a sum of all such G's. When we apply F, we get that the outcome is in the sum of some F after G's, which are maps from M to K. This means the trace is a functor. Next, assume that F from N to K is an injective morphism. Then, for any G from M to N, the morphism F embeds the image of G into K, because F is injective. And so F also embeds the trace of M in N into the trace of M in K. And in other words, this means that the trace of M preserves monomorphism. Unfortunately, the trace of M is not left exact in general. Here is a counterexample. Let R be the path algebra of the following quiver, so we have two vertices 1 and 2, and one arrow from 1 to 2, over the complex numbers. Consider the short exact sequence 0 goes to L2, goes to P1, goes to L1, goes to 0 of R modules. And take as M the projective module P1. If we apply the trace from this projective module P1 to our short exact sequence, we get the following complex. 0, there are no homes from P1 to L2, so again 0. Trace from P1 to P1 by the identity map is just P1, and trace from P1 to L1 is L1, because there is a surjective map from P1 to L1, and then goes to 0. This is the complex which we get, and unfortunately this complex has homology at P1, and this homology is L2, because this L2 disappeared here. So this means that this functor is not left exact in general. Problem 6. Prove, using properties of the Hom functor, that Z2 is neither projective nor injective abelian group. Solution. To prove that Z2 is not projective, we show that taking Hom from Z2 is not an exact functor. This is an endofunctor of the category of abelian groups. Indeed, consider the short exact sequence. We start from 0, we go to Z2, then we multiply by 2 to go to Z4, and then we project onto Z2, and we go to 0. Applying Hom from Z2 gives the following. So 0 goes to Z2, there are Z2 Homs from Z2 to Z2. Unfortunately, there are also Z2 Homs from Z2 to Z4. We can send the generator to 0 or to 2, nothing else works. So we have Z2 in the middle, and then Z2 again as a third component. And the first connecting homomorphism is the identity map, while the second connecting homomorphism is 0. And this means that this sequence is not exact. This is the magenta part is the homology of the sequence. And this means that Z2 is not projective, because taking Hom from a projective object sends exact sequences to exact sequence. Similarly, let us show that Z2 is not injective by showing that taking Homs into Z2 is not an exact function. We consider the same starting sequence. That 2 goes to Z4 by multiplying with 2, and then it projects onto Z2. Applying Hom into Z2 also gives us Z2 at all three non-zero positions, and the first homomorphism is 0, and the second homomorphism is the identity map. And again, now we have a homology at the first position, so this sequence is not exact, and so Z2 is not injective, because Homs into an injective object send exact sequences to exact sequences. And this completes problem 6. Problem questions. Problem question 1. Check that the following sequence where Z15 is in the homological position 4 is a complex and determine its homology. We have 0 goes to Z, multiplying by 4 we go to Z, multiplying by 5 to Z10, by 15 to Z25, and by 6 to Z15, and then to 0. Problem question 2. Is any short exact sequence of abelian groups homotopic to 0? Problem question 3. Construct all projective resolutions and injective co-resolutions for simple modules over the path algebra, over the complex numbers of the following quiver. So we have the vertices 1, 2, 3, and 4, an arrow from 1 to 2, an arrow from 2 to 3, and an arrow from 4 to 3. Problem question 4. Prove that taking the trace from a projective module preserves surjections. And problem question 5. Define and investigate the proper categorical dual to the trace functor from problem 5. Thank you very much, and that was the last lecture of this course.